Welcome everyone to this issue of Careers in Technology. And today we have Anna Garcia Armada. I'm very excited to welcome Anna. Anna is an IEEE fellow. She's currently a professor at the University of Carlos III in Madrid, Spain, where she has served in a variety of management positions: head of Signal Theory and Communications Department, Vice Dean of Electrical Engineering, Deputy Vice Chancellor of International Relations. She is leading the communications research group at this university. She's been a visiting scholar at Stanford University, Bell Labs, and University of Southampton. She has participated and coordinated a large number of national and international research projects, as well as contracts with industry. She is the co-author of 8 book chapters on wireless communication and signal processing, and she has published, my goodness, all right, we're going to skip this. We're going to move on. Anyway, I'd just like to welcome you, Anna, and I look forward to your presentation and to the lively discussion that we'll have today.
Very nice. Thank you very much for the kind invitation. It's going to be a pleasure to share some ideas. Let me see if I can share my screen. Yeah, now I think you can see it. And let me make sure that there is nothing obstructing the view here. Okay, I think you can see it well, right?
It looks excellent.
Okay, so I thought I would share some of my views about what the future of communication may be, looking towards immersive communications. And I usually do research in the physical layer, but based on some collaborations, I can share also my views about the whole end-to-end system design. And that's what I would like to do today. And to do this, let me check if I can get rid of the bar of the Zoom that is showing here, because otherwise it is like in the middle of my presentation and I don't see well. But I think you don't see it, right? So for
We
you,
don't
it's
see it. No,
okay.
it looks quite nice.
Okay, but then I need to make sure that it's not in the middle of everything. How to do this, I'm not sure. Let me check. Okay, I don't see any minimize
No, it
button
looks
here.
perfect from my view. Anyone who has a problem viewing Anna's tables, her presentation, please let me know in the chat or unmute
Okay,
yourself. Let me know.
okay, so I think we can continue. Usually I have 2 screens, but today I don't. So, okay, so how can we advance towards immersive communications? And that's the question I would like to start by reviewing. Of course, I'm going to see this is challenging, right? So communication networks today, we're going to see if they are able, but probably are not able today yet to provide these immersive communications. We need to see what are the key performance indicators that we need and understand if we maybe perhaps need a new generation of communication systems. Now, this topic is very multidisciplinary, and we are going to, for sure, need a holistic approach. And I'm going to try to explain a little bit what I gain from interaction with industry and to explain why we need this industry-academia collaboration and also a holistic end-to-end viewpoint of the design of the communications. I also think that to approach such a difficult topic, we need a joint effort. So we need to create and share our knowledge. And I'm going to touch a little bit upon this in my talk. And I think it's incredibly important to know what the users are expecting and to try to fulfill their expectations. And in that regard, I think maybe we failed a little bit with 5G because not everybody is feeling like 5G was great to improve their lives. And we need to try to improve in this regard, I think, for 6G. So where we are starting from, we are starting from 5G. And 5G is something that is being deployed, and well, we have already service of 5G in many places. 5G originated to be able to cover three different kinds of services that are very, very different. One is enhanced mobile broadband, that is probably the evolution of what we always have been doing with mobile communications, that is provide as much data rate as possible on the move. But 5G also provides massive machine-type communications, and very interesting for the conversation we're going to have, also somehow ultra-reliable, low-latency communications. So 5G already can do a lot of things, and actually, to explain what I think 5G can already do, I wanted to share an example of a project. It's called AMATISTA. I worked in this project with Nokia in Spain, and we provided an immersive music therapy application based on virtual reality in a nursing home. I think this project has a lot of the ingredients I was mentioning, and especially to have the users at the core of our designs. We used 5G, 5G new radio, and we use millimeter waves that I'm going to explain. They are not available everywhere yet, but the project was interesting to understand what we can do with this new technology, to validate a little bit what are the key performance indicators, and to have a very nice application where we can easily interact with users and see that we can improve their lives with these communications. So this is a video. I don't know if you hear it, but the sound is not important because the sound is just music. But it is showing what this AMATISTA project did, and you see here this nursing home, and these people are immersed in the times when they were young, listening and watching the kind of music they used to listen at that time. And that this is the millimeter wave link, fixed wireless link using 5G that we deployed. And here you can see how happy they are. And this is something I wanted to show because, well, not only we managed to get a very good response from them, and this is important because these people have starting to have some neurodegenerative diseases, and it was very important for them to interact, and this was a success. But also we tried, this new technology and saw how it could solve this problem. Now, what are the main key enablers of this project and of 5G as a whole, and how could we do this virtual reality with 5G? Important ingredient is the bandwidth. And to be able to have a lot of bandwidth, we needed to go to higher frequencies. And this is where more higher availability is there, right? But because we went to this higher bandwidth, we needed to do a powerful beamforming, because otherwise we have this big path loss that we need to compensate somehow. Another interesting thing is we have a network slice. So we could have a part of the network completely dedicated to this application. And because of that, we could guarantee a certain quality. And also very important, we have the computing very, very close to the venue where we wanted to do this application, what is usually known as multi-access edge computing, that is important to have very low latency. And all this is already there in 5G, and we can do this virtual reality, but this is only virtual. They were only watching. They were watching all around, but only watching. Now, we want to fully experience, not only watch, be kind of immersed. And for example, if we have our hands, see our hands, and our hands should be occluding what is after them in the movie, because we should feel like this is real, right? So again, with Nokia, in a continuation of this project, we try to understand what kind of processing we need to do to have a fully augmented reality, not just visual, or visual, but with interaction of our own body, and to define what kind of things need to be done and where they can be done. Because there are some things, some processes that can be done in the headset, in the device that the user is using. But I mean, this headset is not going to have a lot of capabilities for computing. So there are other things that need to be done in the edge server. So close enough because of the latency, but in some powerful computing device. And some other maybe don't have all these requirements related to latency and maybe have a lot of computing needs, and they can be done in the cloud server. And we wanted to understand also what kind of capabilities needs the wireless network access network to offer, so we can do this. So we made a study, depending, of course, on how much of these processes you are going to offload to your edge and cloud servers and how much you can do in your own device. It depends also on what are the capabilities of your devices, of the computing capabilities. And we found that if you have, like, let's say, regular processors, this can be quite demanding for the radio interface in terms of what is the peak throughput that you are going to need, that can be gigabit per second, and in terms of the latency, that can be very small, even below 1 millisecond. But if the processors are, let's say, state of the art, so the best you can do today, we still can do this with 5G. Because the data rate is going to be around 1 gigabit per second. This is big, but it is possible. And 4 millisecond latency is also something feasible. So we defined an architecture that could be capable of doing all these things, where the 3D reconstruction is going to be done far away in the cloud, because this is very powerful, computational consuming, but not latency demanding. A lot of things like the hand tracking, the object recognition, occlusion, simultaneous localization and mapping, being able to navigate the environment, this can be done and should be done closer in the MEC. And then we need a very strong link that can be done with 5G, choosing the adequate configuration. And this configuration is a TDD configuration. There are several that prioritize the uplink, because we need a very powerful, strong uplink with a subcarrier spacing that maybe you are familiar in 5G, you can choose. It's called the numerology. And with a numerology that is rather high, 120 kilohertz, that allows low latency, and with a high bandwidth of 400 megahertz that is possible in millimeter wave, and with the proper, RAN resources and network slices, this can be done in 5G. Now, also, we were lucky, to be able to try this in a network, because this was in a collaboration with Nokia. But what if you don't have a network? So we were trying to find some radio access network emulator where you could try to test these kind of things before they are actually deployed, because not everybody has the 5G millimeter wave infrastructure deployed, right? But we didn't find any RAN emulator that could handle in real time actual IP traffic with very high data rates and a lot of users. And then what we did is we developed one. And I put it here because if you need, now we have this emulator, is called Ficore, and you can download it. It is open access, and you can try the same things we have been trying with some emulation of the 5G. Well, we have evaluated this with measurements. It matches quite well the measurements. It matches quite well simulators that are state of the art. So it's ready to be used, and you can use it if you need. And it can actually treat in real time quite a high number, hundreds of users simultaneously. So this is nice. So, well, this is something we have done. So, but question is this really immersive? because wireless communications, mobile communications, until now, have taken care of hearing, and they have taken care of sight. So we can hear, talk, see, watch, but we have more senses, right? And these are nice pictures in El Prado Museum in Madrid. So also I wanted to call your attention that if you happen to have the time to visit Madrid, El Prado Museum is very nice. But I mean, we have smell, we have touch. What happens, with these other senses? Can we really have immersive communications where all of them can somehow become part of our communications, and some of them are really important, especially touch, I think, is really important for the communications between humans to be fully successful. So what I think we need to go in this direction, and maybe 6G could go in this direction. Maybe we will get there, not maybe in 6G, maybe in 7, but we at least need to start going through this path. We need several things. We need even more bandwidth, and more bandwidth we can find in very, very high frequencies, even though these high frequencies like terahertz are complicated because of the propagation and because of the very state-of-the-art technology that is maybe not even ready today, but we can already start going in this direction. But interestingly, bandwidth is not only in these high frequencies that are extremely challenging for technology. We have also very high frequency that is the visible light, what we call visible light communications, optical wireless. And I think, well, there's been a lot of research in this area, but maybe it's not mature enough to be part of a whole wireless mobile communication generation. But we should not forget this bandwidth, because it's a lot of bandwidth also, and it is much easier and much cheaper and much less bulky than equipment that is used for terahertz. So this is also interesting. In any case, in all these frequencies, if we go to higher frequencies especially, we have the problem of the attenuation. So we are going to need MIMO, we are going to need a lot of antennas, and actually we are going to need many, many antennas. So the evolution of MIMO that we foresee, it could be like an ultra massive MIMO that is also easy or made less difficult because of the high frequency that make the antennas more compact, so we can have a very dense amount of antennas in not such a big place. What else we may need? I think we may need to reconfigure somehow our transmitter receiver, and many people are thinking about reconfiguring the channel, which is what usually is called RIS, reconfigurable intelligent services. I'm going to talk in brief about what is my vision on reconfigurability. But before I go to this, I want to also express the important aspect that all these advances need a waveform that is going to convey the information through the visible light, through the terahertz, to whatever we use. And waveforms are an extremely important element of a new design. And I'm going to talk more about the waveforms in the next part of my talk, because this is actually a topic where I do a lot of research. But before that, let me tell you a little bit about this reconfigurability. And I want to ask you, what is the element of the transmitter receiver that has not been really made reconfigurable until now? Because most of the elements of transmitter and receiver, we have made them software, and in software you can reconfigure everything you like. But there is one thing, that is the antenna, and the antenna has not been reconfigured much, but we are working on something that is liquid antennas or fluid antennas, where you could have the freedom to reshape your antenna as much as you want, depending on what you find in the channel. And I believe this would be more interesting, because reconfiguring something at the transmitter or at the receiver is easier than reconfiguring something that is somewhere else, where you need to convey control information. And if you need to control often a lot of elements that are away, this is going to consume also a lot of bandwidth that is going to decrease your throughput. While in the transmitter or receiver, usually you have all this information. So we are working on it. And here you have a video of a first prototype that we had a couple of years ago. We are working on a better one. We're increasing the size of the antenna. It is a monopole. And putting more liquid, you see we're changing the resonant frequency. And here you see the drop of liquid metal that is moving. And very interestingly, we are moving this liquid metal without any mechanical thing, without any pump, because of course you don't want a mobile phone with pumps, right? But we are showing here that you can even move it with an electromagnetic field. So it should be possible to use the same signal you are using for communication and put some bias and also reconfigure your antenna. But of course, this is work in progress, and well, we still need a lot of work on this. But I wanted to mention that because I think this is a way, something worth investing a little bit of effort in research. And the last very important ingredient for this Internet of the Senses and this fully immersive communication, if we need to fully navigate in a world that some part of it is going to be real, but some part is going to be virtual, we need to be able to position ourselves very well among the things that are around us. And this needs a lot of sensing. And to be efficient, we need to do this sensing jointly with the communication, what is usually called integrated communication and sensing, or joint communication and sensing. So we should think of elements of the communication that somehow can be also used at the same time for sensing. Otherwise, we are not going to have enough frequencies to do all the sensing and the communication with so many users at the same time. And then this brings me to 6G, because, well, we are now at the moment when every 10 years we think of a new communication. And by now we have clearly identified what are the challenges that should be solved in this 6G for this immersive communication and for other things that people would like to do. And there are of course challenges related to the architecture. For example, there is the new Open RAN that is going very fast, and then there are many operators interested in this new kind of radio access network architecture. And there is the cell-free that is a new paradigm in the design of cellular networks without cells. Of course, there is AI that should be an integral part of the architecture, and we would like to have ubiquitous coverage that requires satellites or drones to be part of this communication system in a kind of a 3D network. There are also very important social challenges, because this should be for the humanity, for the people, and more we are concerned about the energy efficiency. So our technologies, our solutions should be really energy efficient. And of course, people want high bit data rate, but we don't have so much spectrum. So that means that somehow we need to be able to use spectrum in an efficient way, right? And we need reliability, of course, to be able to trust all these things that we are doing. But very much I would like to focus on the technical or technological challenges. And I mentioned some of them, right? The reconfigurability, the ultramassive MIMO, the sensing and positioning. And it is very important to note that the waveform has an impact in almost all of these challenges that I am mentioning. So now I want to focus the last part of my talk on this waveform. What are the challenges of 6G? Some of them are already identified by the International Telecommunication Union that has already a vision. of where we should be in the 2030 year. And among this vision, there are a lot of challenges or requirements that have an impact on the waveform. For example, we should have very high throughput, talking about 1 terabit per second, and everybody should experience at least 1 gigabit per second. And this is really, really high. And this requires spectrum availability that I was mentioning, right? And this is only available at higher frequencies. Maybe we don't need to go as far as millimeter wave or terahertz. Maybe we can stay in what is called the centimeter wave, also called FR3, frequency range 3, from 7 to 14 gigahertz. But still, these high frequencies are more difficult to amplify. They are more severe in terms of radio frequency impairments. And this has an impact on the waveform that can be used there. It should be resistant to all this. The end-to-end latency, we want it to be very small. And at the same time, we want very high speeds of the things that are around us. We should be able to move in some vehicle, I don't know, this probably is a LEO satellite, that goes 1,000 kilometers per hour. And things should work at these speeds. So this is important for the waveform because low latency, high speed is calling for short symbols. But usually in the past, we have been using a waveform that has actually long symbols. So we need to rethink a little bit this and how this channel variability is going to impact our channel estimation, our intercarrier interference, and things like that. And then last, I mentioned already this localization, this sensing. It has to be very precise, and this calls for some kind of waveform that allows to integrate these communications with sensing. So, of course, with all this in mind, logically, the question arises, can we still use the same waveforms that we're using in 5G or 4G, or do we need a change? So to answer this question, first of all, we need to think or recall what is the waveform we are using in 4G, 5G, and it is OFDM. And why is this the waveform that is used in these standards? It is because of several reasons, right? It is robust to multipath propagation, and when we go to broadband, we are always going to have this multipath. It is very easy to implement with a fast Fourier transform, but it has many disadvantages that with time, somehow we learned how to mitigate, like phase noise, synchronization, very high peak to average power ratio. That means peak signal peaks that are very difficult to amplify, out of band emissions. There are many problems, but despite these problems, and not all of them have been fully solved, but despite that, OFDM is used everywhere, and especially in mobile communications. And I think the main reason that today we use this OFDM is that it allowed us to understand and design our communications in a grid that we call the time frequency grid, where we can very easily multiplex users in the time domain and in the frequency domain with a scheduler. That is something that very easily allows us to obtain and exploit multi-user diversity, and that manufacturers know very well, operators also know how to use, and we need to keep this because nobody wants to give up on this opportunity to use very easily this multi-user diversity. But still, we have all these problems. And another problem is OFDM is not good when the channel changes very fast. All those, maybe until now, we have avoided, maybe saying, okay, we don't move very fast, or we amplify non-linear, linearly, but maybe it is a time to revisit some of these and see if we can do better. And the last years, I've been trying to revisit all this and try to see if we can do better. And so, for example, we can revisit this problem of the peak to average power ratio that would call, ideally for some waveform that is constant envelope that OFDM is not by any means. And to solve this, there was already in 4G a proposal that is part of the standard, and it is actually what our phones are doing in the uplink, because our phones really need to amplify efficiently, otherwise we run out of battery. And it's called single carrier FDMA, also sometimes it's called DFT spread OFDM. But this waveform is not really a single carrier, and it is for sure not constant envelope. So, well, it is a solution, but it's not really solving completely the problem. But there are a couple of new modifications of OFDM. They are called constant envelope OFDM and FM, frequency modulation OFDM, that are truly constant envelope, but they are still OFDM. So we can still use all these nice features of OFDM, but at the same time have a signal that is completely, fully, really constant envelope that we can amplify with no problem. But of course, there is always a con. And these new waveforms lose half of the bandwidth. So these waveforms are only a good solution if you really have to amplify strongly, or you add, for example, in millimeter wave, very high frequency, where you have a lot of bandwidth, but you don't have power. So in these situations, these waveforms are ideal because they are going to give you power at the expense of consuming bandwidth. And here is an example of what is the total degradation that you get because of the amplifier, the nonlinear amplifier in OFDM, which is pretty bad. I mean, the best sweet point you can find is around here, which has a big degradation of about 8-9 dB. This is what you can get with a DFT spread OFDM. You can see it is better, but it is what? Maybe 4 dB better, not something amazing. But you can have zero degradation with these constant envelope modulations that are, a very interesting proposal. So something can be done. Now, I would like to revisit as well this high mobility, because until now, what we said is, okay, let's not move too fast. But what if we want to move fast? So it turns out that this FM OFDM is also a very, very good waveform when the channel changes very fast, because it is doing something like a differential modulation. What we do here is we have an OFDM. This first thing here is what you usually do for an OFDM, but here you are going to put we are going to add one sample to the next and put this into the phase of the carrier. So we need this information to be real because we're going to put it in the phase, and that's why you need to do something in your source, and that is what is going to consume half of your carriers. But you gain this constant envelope, and because of this addition of samples that at the receiver needs to be removed by a difference, this is kind of a differential modulation, and this is extremely robust when you have Doppler, when you have movement, and also when you have phase noise. So when you have things that change in time, this FM or FDM is going to have these effects confined in the low part of the spectrum, because these phenomena usually are not a very high bandwidth. And by just leaving a few subcarriers that we call cutoff frequencies unused, and it can be only one, you completely overcome phase noise, Doppler, without even needing to estimate the channel. So it is extremely interesting if you had flat fading. If your channel is not flat, you need to estimate the channel as you usually do with OFDM. But sometimes the channel is very close to flat. For example, in high frequencies, when you have a very narrow beamforming, you really cannot have multipath there. So it is ideal for this kind of high frequencies, and you can move. You can see here that you can go 1,000 kilometers per hour, and this FMO FDM works perfectly. It even has some benefit of the speed as compared to lower movement. So it is really nice, and it can also work very well when you have phase noise. So it means, well, there are things that can be done, with modifications of OFDM. And for example, if you have a non-terrestrial network and the 3GPP has some recommendation of channels that are very high speed, have phase noise, have a non-linear traveling wave tube amplifier, and FM OFDM is ideal for this kind of situations where, on the other side, normal OFDM really doesn't work very well. And this brings me to another thing, that is the channel estimation, because I mentioned that, well, in general, you need to somehow estimate and compensate the channel. And this channel is usually compensated in OFDM with something that is called pilot simulated modulation. That means that you are going to have your time frequency grid, and in some places in the time and frequency, you are going to have some pilots. Now, this can work very well in OFDM, but not necessarily in these new waveforms that I was mentioning. But there is another way to estimate the channel. It's called superimposed training, and you are going to have data all over your time and frequency, and you're going to have pilots all over your time and frequency. But pilots and data may interfere, and you need to somehow think of ways to compensate this interference, or maybe think of ways to superimpose these pilots in some way that is not going to damage your data. And we have done this for a couple of waveforms. For constant envelope OFDM, we designed a way to inject pilots in the phase in a way that you get a performance that is extremely close to the perfect channel state information. And for other kind of filtered OFDM, we have designed some way to put the pilots in places where the spectrum of the signal is reduced, because OFDM usually is very flat, but these other kind of waveforms, and this happens also with FM OFDM, you can have, the possibility to put pilots in places that are not impacting on your waveform. Another thing you can do is not necessarily estimate the channel, because usually what we do is we send some pilots, we look at what the channel has done to the pilots, and we estimate what happened to the channel, to the signal in these pilots, and use it in a coherent way to recover your information. But maybe we don't need to do coherent communications. And actually, we have done some research on the ways to combine an idea of not knowing the channel at all, not even at the receiver, with massive MIMO. And when you do this, it is a very good match, because the massive MIMO, when you have many, many antennas at your receiver, you can get rid of interference, and you may not need this channel estimation. I had here some examples of things we have done, but I'm going to go a little bit faster in this, because otherwise it would be too long. But well, we have been doing some experiments, simulations, to see how you can combine maybe coherent and non-coherent ways and have less pilots, much less pilots than what you would need with a normal communication. And the last thing I want to revisit is precisely this advantage that I mentioned of the OFDM, that is the time frequency grid. Why? Because now that we think of grids and that we realize that it is possible to have, via transformation like an FFT, a time frequency or whatever, maybe for the ISAC, it is interesting to use a different frame, a different grid that could be the delay Doppler grid. And this can be done with a new kind of multi-carrier modulation that is called OTFS, that works in the delay Doppler instead of the frequency time. And why is the delay Doppler interesting? Well, because this is what we actually do in radar. The delay of the channel is going to tell you where how far in time and also in distance are obstacles around you. And the Doppler is going to tell you the velocity of these obstacles. So if you estimate your channel in the delay Doppler, at the same time, you are sensing your environment. And well, OTFS became popular. There are other multi-carrier variants like orthogonal delay Doppler modulation. There is also DFT spread OTFS because OTFS is also not good in the peak to average power ratio. And we have been recently analyzing how you can do this. So the thing is, instead of having your time frequency, you can have your delay Doppler. All you need is the right transformation here. And it turns out that there is a transformation that is called the discrete Zag transform that is going to move from the delay Doppler to the time. And you can do the same things you were doing in OFDM, but with the delay Doppler instead of frequency. We have been understanding how to estimate the channel, also with superimposed training. And with this same channel that you estimate, you can detect if there are obstacles around, and you can detect where in the sense of what distance and what speed. So this is also interesting. So after all this revisiting, I hope I have convinced you that, well, there is not one size fits all. There are waveforms or modifications of OFDM that are better for the amplifier or for the speed or for the sensing, but all of them are pretty similar. All of them share this discrete Fourier transform or inverse or direct fast Fourier transform architecture. So it should be possible to have some flexibility and allow possibly some precoders or decoders or postcoders that can change a little bit this structure of the OFDM. Also, it should be possible to distribute in the different ways the pilots, and we should be able to have solutions that can be applicable to many, many different scenarios. So in summary, I think we can conclude that it is very important to understand what are the requirements, what can be already done, with 5G, because many things can already be done with 5G, as I showed, but there are others, of course, that cannot. It is very important to have collaborations, to try to understand a holistic view of all the communication system, because we need many different expertise to be able to do this, create and share knowledge, like, for example, the emulator and the data sets that I mentioned, and have the users always, in mind, because, the smile of the users, I think, is something, at least for me, it is very rewarding when you see the impact of the technologies that we are developing in people's life. And of course, flexibility is also a very important ingredient. And with this, I conclude, and I would like to, of course, thank you. And I think maybe I'm going to stop sharing, because otherwise I don't see you. But if needed, I will share again if I need to go back to my slides. Thank you.
Thank you so much for this very interesting presentation. I'd love to know if you're planning a technical document to teach people, like so that you can have chapters teaching each of these important features of communication. I'm also very anxious to see that some of the methods you describe could be put right away into standards, so it can facilitate developing the next generation of what you've suggested here. What are your thoughts on this?
Well, I never thought about writing this down. I mean, part of it is, of course, in articles, and we're writing actually one about the waveforms that is going to go to the communication standards magazine. That is an important ComSoc magazine. But what I try to do is give talks when I am invited, so people get to know. I think it is probably more interesting to listen and see than to read this kind of thing. But well, you never know. You never know.
I think that many students benefit from having this handy in a format where it's outlined and that there are sections, and then you can use this technical document and download it from Explore, just by itself. And the students can have an opportunity to put in their pieces, right? I mean, I think a lot of people find those to be very handy. And also, I think you touch upon some of the other important technologies that we know about from Bell Labs, for example, like the sensing vital signs technology, right? So using Doppler to measure things other than what's obvious really gives you this immersive experience that you're describing, right? And yeah, and so these threads have a very robust set of content available also, where people can really learn about how to architect the future, but to make it accessible information right now so people can.
It's a good idea. I will try to have something written. Yeah, I think it is a good idea. And yes, I mean, there are so many different disciplines that are needed. That's why most of this work I collaborated with Nokia in Spain, because I collaborated with others, with Vodafone, with Huawei, with many people, but in particular these projects, because I mean, we need a lot of different expertise. Otherwise, you cannot reach to have not even the insights of what the whole system needs. And I think this is interesting to, because I particularly am an expert in the physical layer, but what I learned working with others allows me to have a more clear vision of where we should go. Yes.
And it
And the
also provides
standards,
these.
sorry, you mentioned the standards.
Yes.
Um, this is quite difficult because we never know exactly how to reach to those people that are doing the standards. I think there are some fora where we get closer. I mean, some kind of conferences where industry people come. We try to do this also, in Globcom and ICC in the industry track. But it is important to try to create venues where it's easier to put in touch those people in industry that are close to the standards and the research ideas, so we can cross fertilize. Yeah.
Yeah, I mean, like Bluetooth comes to mind, right? So there was a consortium of people who, for whom Bluetooth was a very good incentive, making sure that people could understand and then make a plug and play environment. And many companies benefited. And I don't know if we could imagine the world without Bluetooth right now, and I think what you're describing feels very similar features, where if you could have the architecture, infrastructure, network connectivity you're describing, the OFDM, the FM, all the correction, the peak. What you were talking about, especially that was interesting to me, was just like time of flight type of things, time of flight type of situations that allow you to examine your environment and integrate that information into the experience, which, as you were describing earlier, might have to be done at different parts of the network early on, but over time, as systems improve or applications improve or development tools or even the user feedback about how they want it to work, how that changes and shifts, you may move it to different parts of the network. And those things, enabling those things right now at this moment, or at least laying the groundwork for it, can make great advances, I think, in this field.
Yeah, I know the standards people are looking at this for sure. In 3GPP, in ETSI in Europe, I know there are groups working on this. So there is a consensus, I think, of the way to go.
Yeah.
Now, of course, we need to go, but yes, there are a
Exactly.
lot of people looking at this.
And you're absolutely right. There's nothing that can replace your voice, your presence, your teaching, your mentoring. There's nothing that can replace that. But all these other things help us with our memory. They help us remember what you tell us, and they remember for us. And those things help us even to invite others into the discussion, into the conversation. So I'm very inspired by what you presented. today, and by you, of course. And I'd like to invite anybody else who has a question or comment to please unmute yourself and participate in the conversation.
So my name is Naresh Chand from New Jersey, and I thank you very much for your interesting, very informative talk. My comment and question is that 5G has not been very successful because the operators did not increase their revenues, right? Their revenues did not go up. They did not increase my monthly fee. At the same time, they had to make huge investment. So if they had to switch over to 6G, who will pay for it? How will they recover their investment? Also, when we talk about millimeter wave is line of sight, right? 5G were also based on millimeter wave, but turn out that you can't implement it, right? They have to lower the frequency band. So will you have not the same problem with 6G if you are building a system based on millimeter wave? Because millimeter wave, they have a lot of impairment. Reach is very short, require huge investment. You will have to have a lot of small cells, and at high frequency, the cost of all components and everything, goes up. So sometimes I feel that that 5G did not become very successful because the investment and the originally, they were talking using very high frequency, which did not happen. And when you are at low frequency, then benefit you gain are not relatively much. So, but for your
Yes.
I do not know what is your pressing, use case where you really need it. I mean, if you have this kind of bandwidth, can I digest it? Can I use it for anything? So this is my comment and question.
Yes, it's a very, very good point. I think maybe 5G was a little bit over-dimensioned, maybe hoping for some applications that didn't come. I think it paved the way. Eventually, when these applications come, it may happen that we really need this millimeter wave, but by now, it is not clear that it is needed. And the operators don't want a 6G oversized again. I think they want something that is like very precise, concise. We are going to go to high frequencies, but not millimeter wave. Probably it's going to be the FR3 centimeter wave. Around 7 gigahertz is probably the sweet spot, but maybe a little bit higher, but not super high. So in a way, we will have bandwidth there, but not all the problems of very high frequencies. And that may be, a solution. But by now, there is some position papers of all the operators making it very clear that they want a 6G that is standalone. First, not to go first to non-standalone and then make it standalone. No, standalone from the beginning, energy efficient, and not extremely, oversized. But let's see. Sometimes it is very difficult, because the killer application we never know until it comes. And well, sometimes there are technologies that are developed and maybe it is too early, but they are there whenever it is needed. So, but I think everybody has very clear that 6G needs to be an evolution, not a revolution, and go to the point. Yeah.
And maybe the elephant in the room in the United States is that there's a lot of secrecy, confidentiality about the condition of the infrastructure itself. I mean, there's no doubt that we have significant outages from time to time. We're vulnerable to weather, to disconnection from power grid, from, we have an entire organization in IEEE that's dedicated to going out and providing connectivity and communication during storms. And we don't even broadcast to subscribers how long they can expect their communication to remain intact. So you might have a number of bars on your phone, but you don't actually have connectivity because the backhaul is not there, or some other part of the system has come down. And if you don't have access to those components, then you really don't have any service at all. So maybe the network service providers are trying to hop from lily pad to lily pad for a while to see what's going to go on with government regulators, to see if there's going to be any kind of mandate to update and, proof these systems so that they're reliable, because people are no longer using embedded infrastructure. They're no longer using copper wire like they were before when most of these regulations came about. Now we're facing a world where people are relying on wireless, but it doesn't have, what do they call that? It's not lifeline service. It's not providing lifeline service. And so if it doesn't provide lifeline service, the amount of outages can go up pretty high before anybody's going to complain. And there's no publicly available information explaining to people what the condition of the network or the cell towers is in their environment. So I think until people begin to have more transparency in the infrastructure in the United States, that will be an elephant in the room. That'll be something we have to tackle.
Interesting. I was not aware of that, but I think it could happen that the killer application is connectivity. That could be a surprise. Maybe people just want to be sure that they can connect because until now, maybe people didn't appreciate that so much. For example, 5G, at least in Europe, it brought a lot of coverage. But people maybe don't realize how important this was, and coverage at a price that can be paid. People are not paying more, and they have coverage everywhere. But yeah, it is true that it is not a lot of megabit per second, and maybe that's why people say, oh, but I see this the same as 4G. Well, yes, it is the same as 4G, but here you didn't have 4G, and now you have this coverage, right? So it could happen that being sure that in certain circumstances you are going to have connectivity could be a clear application. We don't know. I mean, let's see what happens.
Thank you. And does anyone else have a question or a comment or another part of this discussion that they'd like to ask about? Okay, I guess I would like to just say thank you very much to Anna and to everyone who's joined us today for this lively discussion. I learned a lot. I'm hoping everyone on this call has something they can take away, some new piece of information. And the video will be available very soon on YouTube. Thank you, everyone.
Thank you. Thank you very much for everybody for attending, and Kate, of course, for organizing this. It's been a pleasure. It's always very nice to have a conversation about our amazing technologies. So hope to see you soon.
I wanted to ask you to leave us with that wonderful vision you have of the future. I just loved it last night, so I wonder if you could share it with us again, just one more time.
Okay. Yeah, well, I think in the future we will be able to provide this communication with our full senses to be, useful for the people. And this is clearly a revolution that it's not going to be the first revolution that we prepare, I think we are using communications engineering to create revolutions. But I think it's going to be, one more step into this amazing technology. So if we have young people watching, I think it is a very nice time to be a communications engineer, and we are going to see very interesting future ahead, where maybe people can embrace, at the distance, or, touch and support each other much better than just with the vision and the voice.
So going back to earlier, I'm sorry I'm extending this call a little bit too long, but I just wanted to remind everybody, we saw these great videos of people participating in a music experience of something that they liked, that they were able to engage with, right? And I think over the years, over this past century or more, since Alexander Graham Bell, who was credited with some of the early inventions of the telephone, right? So many things have changed. Many of those things were envisioned, but their time hadn't come yet, right? And right, and so many of the people who have innovated, like Samuel F.B. Morse, for example, who innovated, almost every one of these innovations has a personal story associated with it, a passion story, very much like Anna is presenting today. This passion story about people having the ability not only to see their loved ones during the pandemic through Zoom, but also to embrace and to have a physical presence, a physical experience. And I think this is the imperative right now that I see, this passion imperative that I share with you. When I was doing my research at ETH in Zurich, I was doing augmented reality, real objects and virtual reality, and people touching them for rehabilitation of the senses that had been impaired during a brain or spinal cord injury. So people who had stroke or some other injury may be having an interruption in their experience of their senses. And so we were combining virtual reality, which is sort of foolproof, right, with the real objects so people can practice in a safe environment and actually have that tactile experience, the senses, other than just the things that you see when you're looking at a television or a movie. So I thank you very much, Anna, for sharing with us this really incredible passion, vision of the future. Thank you.
Thank you.